Hello, today's video is going to be a short one. We're going to discuss the famous bias-variance decomposition in machine learning from a geometric viewpoint. This is a general relation for any sort of regression problem. We actually covered the bias-variance identity in one of our previous videos, link in the video description. But that was for estimating a constant. And based on the comments I received in that video, there seems to be confusion about how this works in a regression setting. So this video is for that. As mentioned, here's the prerequisite video. We will be referring to this one fairly frequently as it serves as, to a large extent, an overarching viewpoint of probability and statistics on this channel. So here's the model setup as well as our objective. We assume that the response variable y has the form f of x plus epsilon. Here y is assumed to be an L2 random variable, that is, y has finite second moment, and f of x is a function of a deterministic variable x. X is known as features in machine learning, or a predictor or explanatory variable in classical statistics. And we have some further assumptions on epsilon. The mean of epsilon is 0, and the variance of epsilon is a constant, sigma squared. And here are some terminologies. F is called the true relationship, epsilon is the noise, and sigma squared is called the irreducible error. It is a measure of the intrinsic uncertainty or limitation in the model. That is to say, if we wish to predict y using x, this is a variation that is unavoidable. Our goal is to estimate the function f from the training data set, which is denoted as D, consisting of finitely many pairs or points with coordinates x and y. In the training data set, all the xi's are considered as fixed and yi's are considered as random. And we denote f hat as the estimator for f. So f hat is a function of x, but it obviously also depends on the training data set. For example, in linear regression model, this f hat stands for the equation of the least square line. And obviously, the least square line is a function in x, and its coefficients are determined by the training data set. And also, there is an implicit assumption, often not spelled out in many textbooks. We treat y and x without subscripts as a new data point. And the epsilon is the unforeseen error. It is assumed that the epsilon is independent, or at the very least uncorrelated, to the training data set. So this perpendicular symbol here stands for statistical independence, but as we shall see, it will take on a geometric meaning very soon. And next, we'll introduce the key definitions in the bias-variance relation. First, we have the mean square error, MSE, also known as the estimated prediction error. And actually, I prefer the latter term because, as we shall see, our identity is really about predicting a new observation rather than only estimating the function f of x. There is a subtle difference between the two. So the MSE is defined as the expected value of y minus f hat quantity squared. And as mentioned, y stands for a new observation. So y is not included in the training data set D. And the expectation operator takes the average over both y and D. That is to say, the randomness in the new observation as well as in the training data set are both averaged out in the definition of the MSE. Next up, we have the bias. And the bias is defined as the expected value of y minus f hat. And once again, the expectation is over y and D. But we can use linearity of the expectation to rewrite this into an equivalent formula, which is f of x minus the expectation of f hat. This is because y is equal to f of x plus epsilon. This relation has nothing to do with D, and we take the average. The epsilon has zero mean, so the first expectation is just f of x. And when we're taking the second expectation, the big Y has nothing to do with that, so this is ED of f hat. Next, we have the variance. The variance of f hat is simply the variance over D of f hat. And this is the result. The MSE, or the estimated prediction error, is the bias squared plus the variance plus sigma squared, the irreducible error. And we'll see next that this identity is a Pythagorean identity. So the question is, how do we set this up? So first, let's consider the ambient space, the universal set H. This is a Hilbert space of L2 random variables that can potentially depend on both y and d. And then we have a vector subspace HD of H. And this consists of random variables that are functions of the training data set only. Next, let's consider y, the new response. Obviously, y does not necessarily lie in HD. Otherwise, y would be a deterministic function of the training data set. This is not usually the case in practice. And then we're going to do some projections. Here's the subspace 1 of constant random variables. This is not only a subspace of H, but also a subspace of HD, because constant random variables can be seen as constant functions of D. As we covered in the prerequisite video, projecting a random variable onto the subspace 1 gives the unconditional mean. So here it is. We know that the expected value of y is f of x, the true relation. But here, the perpendicular component, epsilon, is not only orthogonal to the subspace 1, it is also orthogonal to the space HD. Remember, the epsilon is the noise in the new response, which we assume to be independent to the training data set. And because epsilon has mean 0, if we take any function in the space HD, the inner product between epsilon and that function would be 0. So therefore, epsilon is perpendicular to HD. Remember earlier we wrote epsilon is statistically independent to D. Here, the same symbol takes on a geometric meaning. The epsilon vector is orthogonal to the space HD. Next, we consider an arbitrary estimator. As mentioned, is a function of x and d, and not y. So f hat lies in the space HD. We then project f hat onto the subspace 1. So we get EDF hat that lies in the direction of 1, and its perpendicular component has length the square root of the variance of f hat. The difference between f and EDF hat is the bias of f hat. And finally, we connect the tips of y and f hat. This line segment has length the square root of MSE. So this green vector has 3 orthogonal components, as we can see. The vertical one, epsilon, that is orthogonal to HD. The bias lies in the subspace 1. And the last component, f hat minus its own mean, lies in HD but is orthogonal to 1. By the Pythagorean identity, the MSE is bias squared plus the variance plus sigma squared. And the formal proof inspired by this diagram is now very straightforward. First, we have the orthogonal decomposition. Y minus f hat is equal to y minus f of x plus f of x minus EDF hat plus EDF hat minus f hat. So the 3 components are grouped as such. The first term, epsilon, that's the irreducible error, is perpendicular to HD. The second component lies in HD and is orthogonal to the subspace 1. And the last term lies in 1. By the Pythagorean identity, the square norm of the left-hand side is the MSE, and the square norms of the 3 terms on the right-hand side are the irreducible error, sigma squared, the variance, and the bias squared, respectively. And that finishes the proof. Thank you very much for watching, and I'll see you next time.